The independent variable is the concentration of acid, and you are measuring the volume of gas produced. The way that you do this practical is we measure a certain amount or a certain volume of acid, because that is going to be a control variable. So we want 50 centimetres cubed of acid. You might want to say how you measure 50 centimetres cubed. Obviously it's a liquid, so you're going to be using a measuring cylinder. And you want the same concentration of that acid to start with, because we're going to be changing that. So we're going to start with 1 molar hydrochloric acid. We're going to pour that into a conical flask. Can you see the conical flask here? The reason we're going to do that is because we want to stick a bung in the top. What we're going to do is we're going to put the bung in. We're going to put a delivery tube, which is this thing here, and we're going to connect that to the gas syringe, which is this thing here, which is just a way of collecting gas and measuring it easily. We are going to put a 3 centimetre strip of magnesium ribbon into the flask. Again, I'm being very specific about the size of that strip because the length of magnesium is a control variable. If we change that, we've got 2 independent variables. As soon as I place that in, I'm going to put the bung back in to stop any gas that's escaping, because I want to collect all that gas, and I'm going to start a stopwatch. Every 10 seconds, so you can see I've put a little 10-second thing down here, I'm going to record the amount of gas produced in the gas syringe. And it's not that like you take them away, you're going to just continue to record it. So it'll be like, all right, in 10 seconds there was 15 centimetres cubed of gas, and then at 20 seconds there was 25, at 30 seconds there was 45. So it keeps going up, okay? So you're just recording that gas produced. And then all you do is, that is the main method. So I'll put that on the side. So that's the method that we actually, sorry, not that bit. Steps 1 to 4 is the main method. And then again, we're now going to change our independent variable in step 5. So we are going to repeat steps 1 to 4, but this time we're going to use a different concentration of acid. So we're going to put that in, oh, that's not very good pink. We're going to put that in pink because that is going to be our independent variable. So this time we're going to use 1.5 molar hydrochloric acid. Again, it does not matter in your, if you write a method for this, about the concentrations that you give. You just have to use 2 different concentrations. Right, what might you be asked to do? Well, when you get some results, obviously in the exam you're not going to be recording the results, but you might be given a table of student results. So it's highly likely that they will make you plot a graph. So this one here I plotted, which is based on some sample data that the exam board give us to do in lessons in case it all goes wrong. So you can see here I've got 2 lines on the graph. Now sometimes students do get confused when there is 2 lines placed on a graph. It just makes things a little bit more cognitively funny. There's a bit more going on, so it's harder to work out. And especially in the exam when both lines will be the same colour. So they might use a dashed line and they might use a dotted line, but they'll try and distinguish which line is which. You can see here that I've got 1 molar dm cubed, which is the red line, and then I've got 1.5 molar dm cubed, which is the blue line. So you might get asked a few things. So once you've plotted this, it might say, all right, compare. So you have to say how they're the same, how they're different. It might say compare the rate of reaction for 1 molar versus 1.5 molar. So you can say that for the 1.5 molar, in fact, that's not very good, 1.5 molar, is it? And put the decimal point in there. So 1.5 molar, you can see that the rate of reaction is steeper there, so we can say the rate of reaction is faster. Whereas this one obviously not as steep, therefore not quick. We can see here that they both level out. So whenever we get a flat line on a rate of reaction graph, it means that the reaction has stopped. And that's because one of the reactants, as in the limiting reactant, will have been used up. Okay. Now, it's really common that what they would get you to do at this point might be to calculate the rate of reaction. So they might say calculate the rate of reaction for 1 molar between 0 and 60 seconds. So if that was the case, what you would have to do, let me use a green pen, 0 and 60 seconds, so we would draw a line up at 60 seconds, and what we've created there is now we've created a tangent. Okay, so we could do the change in y, which is rise over run. So we could see that, because rate of reaction is always about time. So in 60 seconds, we produce this amount of gas. So you'd have to take it across. I think you've got an actual value for this. So each one of these squares, I've worked out that there are 10 squares in 20 centimetres. So there's 10 squares between there and there. So each square is worth 2. So this is 1 square below the 40. So this is 38. So we've got 38 of a product, in this case the gas, so 38 centimetres cubed of a gas being produced in 60 seconds. If we do 38 divided by 60, we will get our mean rate of reaction in the first minute. So that's really common, that they might ask you to find a rate of reaction from a graph. Okay, same thing, they could do it with the steeper one. They could ask you to compare them. If they ask you to compare the rates of reactions, they wouldn't ask you at 60 because we can see the blue want to stop, but they might say compare the rate of reactions in the first 30 seconds. So you would just find the rate of reaction here, you'd find the rate of reaction there, and then you could literally give the two different rates of reactions and say one is faster than the other, and that would be enough to compare them. Once you've plotted a graph and once you've done some maths with the graph, the next thing that they'll probably ask you to do is they will ask you to explain the results, and they're going to link this here to collision theory. Collision theory comes up on the chemistry paper 2 pretty much every year, and we're going to go through it in the second part of the session. But collision theory, remember, is about explaining why the rate of reaction would increase or decrease in terms of particles and collisions between particles and the factors that would affect that. In this case, we're explaining these results, and these results were to do with changing the concentration of acid. So when we're talking about our collision theory, we don't want to talk anything about temperature, so therefore we're not mentioning energy. We're just talking about how the concentration would affect it. So you can see here, I've given the sample answer. So increasing the concentration of the acid means there are more. Hopefully, I'm trying to leave a little gap here so you can try and say the answer to yourself. There are more acid particles per volume. This means that collisions between acid particles and magnesium particles, which is the reactant, will be more frequent. So the rate of reaction increases. And the gas is produced more quickly. So that's how we explain it using collision theory. And again, you might get asked to explain this flat line. So explain the flat line in terms of collision theory. So that is, when there are no more reactants to collide, they can't collide. So the reaction stops and no gas is produced. Okay. The second rate of reaction practical. This is the one that you're probably more familiar with. This is the one that's pictures always appears in the revision guide. It's this thing here. It's what we call the disappearing cross practical. Now, really simple practical, but it contains a thing with a very long name, so it sounds hard. You're going to use something called sodium thiosulfate, okay? You do need to remember sodium thiosulfate as its name. So, what we're doing is we're investigating how the concentration of sodium thiosulfate, so that is the independent variable, affects the rate of reaction when added to hydrochloric acid. So rate of reaction isn't the dependent variable. We're not measuring the rate of reaction. What we are measuring is the time taken for this cross to disappear. So that is our dependent variable, the time taken for the cross to actually be visible. And that is a really, it's not a very good scientific point. We like things in science where we can measure with a gas syringe. It's very clear how much gas was produced. Saying when or not a cross is no longer fully visible is a bit of an opinion. So it's very likely in this practical that they are going to ask about source of error. And the massive source of error is different people might think the cross disappears at different points. So you're going to have means that are wrong. And really commonly in this practical, you'll get asked questions where they'll ask you to calculate a mean, and there will be an anomalous, very obvious, don't look for anomalies that aren't there, but there'll be a very obvious anomaly within the mean that you need to exclude. So we'll get to that when we get to more questions. So what do? Again, give values of things. So we want 50 centimetres cubed of 8 grams per decimetre sodium thiosulfate. So the volume of the thiosulfate is a control variable. We're keeping that constant. That sounds really complicated, 8 grams per decimetre. The reason that's there is because we need to do different concentrations of it. Now, you might need to, it is on the spec, know how to get different concentrations. Now, you don't need to know like the exact dilutions, but the way you would get different concentrations is you would start with 1 bottle of sodium thiosulfate, and you might get told, all right, this sodium thiosulfate is 40 grams per decimetre cubed. And all you would have to do is just, you might say you've got 1, 2, 3, 4, 5. You want 5 different concentrations. So what we do is we just dilute it differently. So you just use different dilutions. So I've given ones that we could use in school that the spec gives us. You don't need to know these, but you do need to know that how to get different dilutions. So for instance, if you had 50 centimetres cubed of sodium thiosulfate and no water, then obviously it's going to be the original. Whereas if we take 40 and we add 10 centimetres of water, we've still got 50 centimetres cubed, but now it's got less concentration. There are less grams of sodium thiosulfate per decimetre squared, and cubed, and more water. Again, 30 to 20, 20 to 30, 10 to 40. So we're always having 50, but what we're going to end up with is different concentrations. All right, you do not need to learn, as I say, the dilutions, but you do need to know that that's how you would get different concentrations. Again, we're going to put it into a conical flask. Not this time because we're going to put a bung in it. In fact, that's a key part of this practical. We're not putting a bung in it. The reason we put it in a conical flask is because conical flasks are easy to swirl around, all right? And we need to swirl this, all right, in order to get the particles to collide with each other. Again, that might be a source of error because you might swirl it nice and gently for the first one, and then one of them you might go insane and swirl it really fast, and you're adding energy in, and that could be a source of error. So that swirling is itself a source of error. We're going to put a black cross underneath the conical flask. Notice that I've said a black cross because if you use different colours of crosses, again, you're changing your variable. So the thickness and colour of the cross are going to be control variables in this practical, as is the concentration and volume of acid, which we've already talked about. Sorry, we haven't talked about that one. Not yet. We've talked about the volume of sodium thiosulfate. So with this one, again, massive source of error. If you put a cross under that was a nice line drawn with a biro, and then you get another cross that's done like that, obviously this one here is going to be more visible for longer than this one. So that is another source of error. So you've got to make sure that the cross is drawn at the same thickness and you're using the same colour. We're going to pour 10 centimetres cubed, so that is where we are being very specific about the volume of acid, and all I'm saying here is it's dilute. So we just don't want strong acid. So you can just say dilute acid in your method, or you could say 0.5 molar or 1 molar, that they're classed as dilute. And we're going to put it into the flask whilst swirling gently, and then we're going to start a stopwatch. Again, there's a source of error in here. Okay, we are measuring, I'm going to get into it because I've just seen this question when I was doing a tutoring session earlier. I'm measuring 50 centimetres cubed of acid there, and I'm going to do another measurement here of my, of the sodium thiosulfate here, and then another measurement here of my hydrochloric acid. I've got to use different measuring cylinders for those, because otherwise, if I use the measuring cylinder, or at least I have to wash it out. If I use the measuring cylinder that had the sodium thiosulfate in, and then I don't wash it out, and I use the same measuring cylinder to put the hydrochloric acid in, they're going to start reacting before I've started the stopwatch. So you have to be very clear that you are going to add them, and they've not been mixed at all prior to that point, and you start the stopwatch exactly at the time where you add them. Again, another source of error. What you do is you swirl it gently, and you put it back down, and you're just going to leave it until you decide that you can no longer see that cross. Again, another massive source of error. That's total opinion. You record those results down. With this one, we want to do it at least 3 times because there's so many reasons that this practical could be inaccurate. So the more times we can do it, that's one way that we can try and make it a bit more accurate. We're going to do it as many times as possible. We're going to remove any anomalous results from it, and we're going to calculate means. So you can see here, that's not a very good experiment because I've only done it one time. Again, that's the main part of the method. And then 6 is where we introduce the independent variable, where we're saying repeat it for different concentrations of sodium thiosulfate. You do not need to give the concentrations, you just need to say do it for different concentrations. So, what could we be asked about? Well, we could, as I said, well, they're definitely going to be asking about errors, but what we could be doing, like this one here, is we could be given a set of data and we could plot it on a graph. All right, rates of reactions, you're going to be plotting graphs. So make sure you can plot graphs. When you plot graphs, just make sure that you are totally aware of the scale. So we should look here, we have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 squares equals 20, so 1 square equals 2. So make sure you get your plotting right. Really easy to do that wrong in the pressure of an exam. You would plot this onto the thing. It would always say here, so make sure you plot your data and it always say draw a line of best fit. All right, so once you plot the data on, I am going to have to plot it for this question. So 0.1 is 82, so that's 80, and we know that 1 square is 2, so that's there. 0.2 is 40, so that is here. 0.3 is 20, 0.4 is 13, so that's 10, and it's halfway into there. 0.5 is 10, 0.6 is 8. Okay, so once we've plotted our data, you would have to draw a smooth line of best fit. So don't do any of this. We don't want to do any of this joining of points. That will not get you marks for your best fit line. You've got to make sure that you drew a smooth curve, and it wants to go through as many of the lines as we can, so that will be fine in the exam, even though I've missed one. The way to do that is just to hold your pencil above it and just slowly practice getting the arc right with your arm. Once you think you've got your hand has got the right arc, you just join them. Okay. Now, what it's saying here is predict. So this is trying to find a value that's unknown. Predict the time taken for the cross to no longer be seen at 0.7 moles. We didn't measure 0.7. So what we have to do is we have to make our line of best fit, and we're going to have to extend it to be something like that. And then we can draw our line up and we can find our value at 0.7. So based on my data there, I think it's going to be 8. Okay, maybe actually it should be a little bit lower than that. That one was 8, so maybe we're going to say that it was 7 seconds. Okay. Either way, we can see that the rate of reaction, the time taken, as we increase the concentration, the time taken is decreasing. However, as you increase the concentration to a certain point, it stops being as much of a factor. So just draw a line of best fit, try and keep it smooth. This would be a bit rubbish here. Don't know what happened there with the pencil, but try and keep it smooth, and then you can use it to predict values you haven't done. All right, let's have a look at some questions that we might be asked about this practical. So again, you're going to be asked to plot results on a graph. I'm not going to do that, okay? I'm sure I've just shown you how to plot a graph. You can plot a graph, but you might then be asked how to describe how the reaction changes with time. So let's say if I did, I'm just going to sort of roughly create the lines. So time 0, so if you've got that 0 point, 20 and 48, so that's going to be, again, you need to work this out. So we've got 10 squares equals 20, so 1 square equals 2. So 20 and 48. I am going to have to plot it because of the questions I've asked. 40 and 72, so 40 goes up to 72, which is here. Make sure you plot in pencil, because if you do what I did there, you can just remove it. 60 and 90, that's a nice easy one. 60 and 90. We want 80 and 97, so 80, that's 98 is there, so 97 is here. 198, so 198, that would be on that line, and 120 and 98. So again, we can see we have got a very obvious curve. So I'm just going to join that curve. Again, you can't see, but I am twisting my iPad slightly because when I draw curves, I like to turn the paper to make it fit my hand rather than making my hand fit the paper. So something like that, okay? Now I'm going to cheat a little bit here. This is very clearly a flat line, so I would add that in with a ruler. That's absolutely fine. And then the first bit here, all right, you can do with the ruler as well. The curve you only really need to do for this middle part, so that would be fine. Okay. So describe how the rate of reaction changes with time. So we can see that as time increases, the rate of reaction is actually less steep. So the rate of reaction is actually decreasing. Okay. If we were going to be talking about it properly, we would say, you know, initially the rate of reaction is very fast, between 0 and 20 seconds. If I was probably going to plot that, that would be a bit better. But we could say that it's very fast for the first 60 seconds, then it starts to slow down. Okay, so it slows down from 60 to 80 seconds, and then after 100 seconds, the rate of reaction is no longer increasing, so the rate of reaction has stopped. That's because we're going to run out of one of the reactants. Add a line of best fit to show how the volume of gas produced if the students repeat the experiment with a higher concentration. So a higher concentration, again, this is really common. What they do is they ask you to draw a second line on a graph in order to see if you can you understand how that would change the results. So a higher concentration, there'll be more collisions per second, therefore we're going to have a faster rate of reaction. The key thing is, though, we're still going to get the same amount of volume of gas produced because we're going to run out, we have the same reactants to start with. So if I do this one in red, we need to make sure that our flat line is the same, all right? But we're going to extend it because we're going to get to it earlier. And then all we need to do is we just need to make sure that this is faster. So something like that would be absolutely fine. All right, faster rate of reaction because we've got steeper, but we are getting to the same volume of gas produced. So the reaction finishes. Okay, again, I've talked about this one. Really common that you are going to be asked to link it to kinetic theory. So you're going to have to explain using collisions between particles why. So during the reaction, the rate decreases. Explain in terms of particles. So that's what I've said. The rate is decreasing. So in terms of particles, why is that the case? Well, obviously, if we're talking about concentration, the more that are colliding and reacting, that means that they're producing products. So therefore, we've got less reactants. So we would just say, as the reaction continues, the reactants turn into products. So therefore, the concentration of reactants decreases. Therefore, there are less collisions between reactants every second. Therefore, the rate of reaction decreases. So it's just link, link, link. This one, again, kinetic theory. Temperature also affects rate of reaction. Explain why mentioning particles and collisions. Now, temperature is a bit different to the others because temperature does two things. Mostly, when we're talking about rates of reactions, we're talking about collisions. But with temperature, we're talking about an increase in the frequency of collisions, but also we're talking about an increase of the energy that each collision has. So temperature increases rate of reaction because there are more collisions per second because the particles are moving more quickly. And secondly, the particles collide with more energy. So it's more likely that each collision meets the activation energy needed for the reaction to occur. So that's why temperature is going to speed up the rate of reaction. Something that you just need to know in this practical, why does the cross disappear? It's because you get a solid particulate formed. The solid particulate is sulfur. It's very common in chemistry exams to give you these state symbols. So you can just see here we've got two aqueous solutions, added those together, produce an aqueous, a liquid, a gas, and a sulfur. It's also quite common, they might say, with this set of data here, they might say, why does the mass decrease? I think that question is going to come up in a minute. The mass decreases because one of the products is a gas. And as I said earlier, notice there's no bung in the top of there. Therefore, any gas that is produced, and there will always be gas produced, is going to escape. So the mass of the reactant is going to be less. So the mass of the product is going to be less than the mass of the reactants. You might need to calculate reaction time. So calculating reaction time is really commonly asked. You know, it's a whole topic. It's one of the 4 topics, so it probably will come up. Very easy. You just do the mass of a product or the mass of the reactants that's decreased. Either way, it's fine. Either a decrease in reactants or an increase in products, and the amount of time. So in this case, it would just be 0.725, because that is the amount of product produced, and it produced it in 20 seconds, so that divided by 20 would give us our mean rate of reaction. If they wanted to just get an extra mark out of this, they would ask you to give your answer to a specific number of significant figures. So make sure you read the question carefully and don't lose mark for those significant figures answer. Okay, I've put in a couple of extra questions around this because it's really common, but this means I can spend less time talking about it in the second part of the session, so it's okay that we're spending more time on it. It's the longer practical is more likely to come up. Explain why the mass of the conical flask and contents was greater at the start than at the end. We've already said why. It's because one of the products is a gas, 1 mark. There is no bung in the conical flask, therefore the gas escapes into the atmosphere. So that's why the mass decreases. I told you already you're going to be asked about error. Okay, error is there are 2 types of error. So the first type of error is systematic. That's where the value for error each time is going to be the same. So that's where you would have a problem with a machine. So for instance, in this one, or one of the later practicals, if you're using a balance to figure out the mass, and the mass, so the balance already isn't at 0 when you start, then you're going to have what you call a 0 error, which is an example of systematic error. Every measurement that you take is going to be out by the same amount, therefore it's a systematic error. The other type of error, and this is the one that's more likely to occur in this experiment, is one that's called random. You cannot say human error, you must say random error. So for instance, if the person looking at this each time has a different idea about when the cross disappears, that's going to produce error between results, and therefore it's going to be a random error because it's not going to be the same amount of error each time. Therefore, it's a mismeasurement, we call that random error. So the error here, the student not being consistent in their opinion of when the cross can no longer be seen. What type of error is a random error? Okay. Because there is lots of error in this experiment, as I've told you, you're quite often going to be given a set of results and you would have to calculate a mean, but they're going to be very clear and very obvious about this. 60.5, 63.2, 82.3 and 65.7. This result here is very different to the others. Okay, don't look for anomalous results where there aren't there. They'll be very clear and very obvious in the exam, and they might even say there is an anomalous result, do not include it, like I've said in this question. Okay, if that is the case, then obviously we've only got 3 valid results, so you would just add together your 3 valid results, so 60.5 plus 63.2 plus 65.7, and you divide that by 3 in order to give you the mean time. And for those studying higher, this is an excellent opportunity for the examiners to get you to use the tangent line. All right, so in this case, the exam question has provided the tangent line to us, but you could be asked to draw it yourself. So if they want you to give a mean, as in like an average rate of reaction over a certain amount of time, then you don't need to draw a tangent line. However, if they give you a specific time that they want to know the rate of reaction for, or in this case, a specific volume that they want to know the rate of reaction for, that's where you have to draw a tangent line. So remember, a tangent line, they want it drawn at 0.4, so that's this point here. You can see here that a line has been drawn that touches that point, and is equal in terms of its distance away from the curve on either side. That's what we call a tangent line. And then to calculate a tangent, you just do the change in y divided by your change in x. Change in y over the change in x in order to calculate the tangent. You can extend this line if you don't like the numbers. All right, but you can see here, again, you would have to use the math. So you've got 5 squares equals 10. So if 5 squares, it's probably not good to go with 5 because that's hard to do a division. So 10 squares equals 20. So 1 square is going to equal 2. So this is 4, and this is 12, 14. This is halfway between, so this is 15. So we've got a change here of 11. And over here, we've got 0.1 going up to 0.6. What's each one? So we've got 10 squares equals 0.2. So 10 squares equals 0.2. So 1 square equals 0.02. Okay, so it's going up to 0.6 2. So therefore we've got our change of 0.1 to 0.62. So we've got a change in x which is equaling 0.52. So you just do your change in y, which is 11. So it would be 11 divided by 0.62, and that would give you your rate of reaction for the exact concentration using the tangent. Okay, it's exactly the same as a mean as soon as you've drawn the tangent. It's just changing y divided by changing x. Okay, let's go into our second practical, chromatography. A lot simpler, all right, and only one part of it. Chromatography. Most people are good with chromatography, all right, so what you need to do is, the first thing you do is you get your pencil and you draw a horizontal line on a piece of chromatography paper. The reason we use pencil is because pencil will not dissolve in water, so it can't be dissolved in the solvent, so therefore it will not move. We're going to mark 5 pencil spots. You don't need to say 5, you're just going to mark some spots with a pencil where you're going to place your different inks or your different food colourings or whatever it is that you're looking to investigate. And the key thing is that you must place them at even intervals. So I've said to put them spaced across the line evenly, and you don't want to put them too close to the edge. What we do is we want to put 4 known things there. Okay, this is the bit where people sometimes go wrong. So we've got a known blue, a known red, a known green, and a known yellow. Okay. What we are then doing is we are investigating the colours that are in this unknown brown or whatever it is. Okay, so we've got an unknown one here. Now, because I've used colour, it's really obvious what's happened. But in the exam, remember, these would be black spots. So you would have to figure it out like this instead. And therefore it just adds a little bit more a little bit more difficulty to it. So we've drawn the line, we've put our spots on it. The key thing now is we're going to put our filter paper, or our chromatography paper I should say, sorry, into the water at about a depth of 1 centimetre. Absolutely really important that this water is below all of those dots. Because if you put it above the dots, it's just going to wash it out and the whole thing won't work. So it will just dissolve into the water in the beaker. We need the water, the solvent, to move up the paper so that the water line has to be below the dots at the start of the investigation. We have to put it vertical into it. You can explain how you can hold it on. You don't need to, but I've used a splint, just wrapped it around it, and a paper clip to hold it on. Again, make sure it isn't touching the walls of the beaker. That's going to affect the results. And make sure it's that water line is below the dots. I've already said that. Okay. You then just let the water move up the paper until you get to about 3/4, all right? Until you're starting to get to the top of the paper. Let the water move up it. what will happen is the water will dissolve these different dyes into it. And as it travels up the paper, those dyes will move with the solvent. Okay? We'll explain the results in a little bit, but that's what's going on. This is a step that's often missed out. Once you stop the experiment, so once maybe the water's got to about here, you're like, right, I'm going to stop. You have to look at where the water line was. And you're going to draw a line on to show where the water line is, because that is the distance that your solvent, in this case the water, moved. In order to calculate our F value, we need to know how far the solvent moved. So make sure you include that bit in your method. Okay. So what are they going to ask you? Well, the first thing they're going to ask you is they're going to ask you to identify the colours. All right. So that's what I've said here. That's very easy to do. Right. So we need to know this thing called RF value is just a measure of every colour has got a specific RF value. It would move a certain distance during this practical. So ones that move the same distance must be the same colour. So we can see here that these two are the same distance, and if we look at before, this one was the blue one. All right, so therefore this contains blue. Okay, it's also got the same distance as that. What was that one? Oh, that was the yellow one. All right, so this would contain yellow. There's nothing here, so it does not contain green. We don't know what that is. I'm going to get to that in a second. So it contains an unknown colour. You can see it was pink, but for the exam you wouldn't. So it contains an unknown colour, and it's the same line as that. What was that? Oh, that was the red one. Okay, so it does contain red. So we can say that this brown ink contains a mixture, or a formulation. Remember, formulation is a useful mixture done on purpose at specific values to make something useful. So it contains blue, yellow, and red. It also contains an unknown colour, and it does not contain green. So that would allow us to figure that out. How would we figure out what this unknown colour is? Well, the way you would do that is you need to calculate RF value. So you calculate RF value. Now that's done by doing this. So in order to calculate RF value, what you do is you measure the distance that the solvent has moved. So we need to go from our pencil line to, I'll do this in green, the pencil line which is here. You use a ruler and you measure that which is the distance of your solvent. That's the distance the solvent travelled, and you probably want to be doing this in millimetres. As long as you keep the same units, it doesn't matter. And then, so it might be like, right, what was the RF value of the unknown? So the unknown one went from there to there. So this is the solute, right? The thing that was dissolved. So that's your solute distance. To calculate RF value, you do distance moved by the solute. Okay, so let's say that that was 5 millimeters divided by distance moved by the solvent. So let's say that this was 30. That will give you an RF value, a specific value that colour moves when dissolved in water. If you compare that to a table of known RF values, you'll be able to find the one that it matches, and therefore you'll be able to identify the unknown colour. So that's a common question. How would you identify an unknown colour? All you need to say is calculate the RF value and compare it to common, to the RF value of known colours. That's how you do it. All right. The other thing you might get asked is why? Why does this actually happen? And this is, again, an area people find confusing. We're going to talk about two things. We're going to talk about the mobile phase, and we're going to talk about the stationary phase. As odd as it sounds, the stationary phase is the paper itself. So the paper does not move, it stays still. All right, so the water is going to move up the paper, but the paper stays still. So that is stationary. And then we're going to talk about the mobile phase. The mobile phase is the solvent, because the solvent moves up when you put it in the water. And it's not just the solvent, it's the solvent with all of the different dyes dissolved in it. So this is the mobile. Now, why does chromatography actually happen? The reason why these separate out at specific RF values is because different substances in this mixture, as in the different colours, or the different dyes, or whatever they are, have got different attractions to the stationary phase. What that means is a posh way of saying some of them are more attracted to the paper than others. So some of them are a bit stickier to the paper, all right? You've probably done this. Some colours are harder to rub out with a ruler, all right? If you spill water on your book, some of them dissolve straight away and go away. Other colours, like black, are probably going to stay there, okay? So some colours are going to be less likely to dissolve into the water and more likely to stick to the paper. Other colours are more likely to dissolve in the water. They're more soluble and less likely to stick to the paper. So the ones that are more attracted to the paper are not going to move as far. So in this case, the red one was the least soluble. All right, it was most attracted to the paper. Whereas the blue was the most soluble. Okay, it wasn't attracted to the paper much. It was very soluble, so it went into the water. Therefore, it stayed in the water a long way as it travelled up the paper. That's why it actually happens. So I've tried to describe that as well as I could here and keep it really simple. So if you want to go back and have a read over that, then you can. All right, let's look at what some questions would look like for chromatography. So they might not be really obvious in terms of asking you what, like specifically saying, or what colours is in it, but they're always going to ask you about what colours. So they might just say, what conclusions can you make about the 4 colours in the brown ink? So that's where we would say, oh, well, okay, look, so it lines up with that one, so therefore it contains blue. This one, nothing line up, therefore there's an unknown colour. It contains yellow, and it contains red. So 3 conclusions. The brown ink contains red, it contains yellow, it contains blue. That would be enough. You could say the brown ink does not contain, what does it not contain? It does not contain green, all right? It doesn't contain any green. So yeah, that would be another conclusion. It does not contain any green. You could also say another conclusion, the brown ink contains a colour that was not one of the known colours. So all of those could be conclusions that you could give. Which colour is the least soluble in water? It's green. The explanation why is because it did not move at all with the mobile phase. So it did not dissolve in the water, therefore it moved the least distance. So it was most attracted to the stationary phase, the paper. We might need to explain why. So we've just said here, explain how chromatography separates the dyes in ink. It's not wanting to write your method. You would just say, it would just be a description of this. So you would just say that the dyes dissolve of different solubilities into the solvent, in this case the water, and some are more attracted to the paper. As the water or the solvent moves up the paper, the ones that are more attracted to the paper will get left behind, and the ones that are most soluble will get carried the furthest. That's how we describe it. Okay, we've already talked about calculating RF value, so I've drawn these on for you, but you could just be given this in an exam and you would have to use a ruler. So it would just say calculate the RF value of the green colour, so therefore you need to measure this distance here, which is the distance that the solvent travelled from the pencil line to the top of the solvent front, and you need to measure the distance that the green covered from the pencil line to the end of the green colour. Okay? Distance in millimetres, and then just use the formula. All right? Distance moved by the green divided by the solvent. It's always the same. That will give you the RF value. And you might get asked to identify problems with this method. Always talking about problems. You can see here, this line here is the water line, or the solvent. The problem is, hopefully you're thinking about it right now, the problem is that the solvent is above the different colours. Therefore the colours, you don't have to explain it, but the problem is the solvent is above the colours at the start of the investigation. So therefore the colours are just going to dissolve into the solvent, not move up the paper. And the second thing is what they've said here, the start line is drawn in ink. So the problem with that is that the start line will dissolve and move up with the paper. So therefore you won't be able to find an RF value at the end because you don't know where the colours started. Okay, so that is going to be the two issues that we've got with that. All right, final practical, purifying water. It is 2 parts, but it's 2 very quick parts. Okay, the first part is analysing. When we're talking about analysing a sample, we're talking about how do we find its pH. That's pretty straightforward, find the pH. You just get a sample of water and you put universal indicator paper in it. The reason we're using universal indicator paper is because we don't want to add anything into our sample and any more dissolved solids. So we're using paper because we can just dip it in and pull it out. All right, it will change the colour of the universal indicator paper, convert it to a pH scale, find what the pH is. So that's how you find the pH. Very simple. Next, what we're going to do is we're going to see how much solid is in our different samples. So we're going to start out with, I don't know, 3 samples. All right, we might get a sample of water from your tap water. We might go to the sea and get a second sample of water. And then we might go to the shop and buy ourselves a bottle of lovely Evian mineral water. And that'll be our 3rd sample of water. So we've got 3 different types of water. Obviously, we need to have the same volume of each, so you just get a measuring cylinder. Again, use a clean measuring cylinder because otherwise we don't want to contaminate them. And we're going to measure out 10 centimetres cubed of each of them because that's going to be a control variable. We need to have the same volume of water. What we're going to do is we're going to get one of these things, which is an evaporating dish. And first off, we need to find the mass of the evaporating dish. So the way we do that is we just place the evaporating dish on a balance and we're going to find out. So in this case, we can see that the mass is 12.2 grams. Then what we do is we pour the 10 centimetres cubed sample of water into this dish. And we place that dish on top of a Bunsen burner. So obviously we need a tripod, we need a gauze. And you're going to heat it till it boils and most of the liquid evaporates and you're going to just be left with the dissolved solids. Okay, we don't need to go all the way, otherwise we might get some of it might get spat out. So we're going to heat it until most of the water has gone away. All right, and then we're just going to let it cool. At that point, the rest will evaporate off. So we're just going to be left behind with some dissolved solid in there. Okay, then once we've let it cool, we put it back on the balance again. This time it's got the dissolved solids in it. And this time we'll get a reading of the mass of the basin and the solids that are in it. So this time it's 16.45. And all you need to do is you just need to find the difference. So we would do 16.45 minus the original measurement of the dish so that we can see that the solids contained in the dish was, and you would do this on a calculator, you wouldn't do it in your head like me because you don't want to make any mistakes. All right, what's that, 4 point, I'm sure you have all just done a maths exam today, will be screaming out why I can't do this. Is that 4.25? I think that looks right. I'm going to say it is 4.25 grams. So the mass of the dissolved solids was 4.25 grams. And then, again, this is the actual method to calculate the mass of the dissolved solids. And then this final bit here is how you are going to investigate as your independent variable. So we are doing different samples of water and make sure we're doing 10 centimetres cubed of each one. So you would do your tap water, find the dissolved solids in that. You would do your seawater, find the dissolved solids in that. That should probably be the most because of all that salt. And your mineral water to find the dissolved solids in that. That is the first part. It is analysing the water. The second part, once you've analysed the water, is purifying it. All right, before we do that, I just want to talk a little bit about what potable water is because it confuses a few people. Potable water means that it is water that is safe to drink. That's all. It doesn't mean it doesn't contain anything else. It isn't necessarily pure. It's just safe to drink. There is nothing in it that will make you unwell. All right. The difference between that and pure water is that pure water contains nothing else. It does not contain any salts, it does not contain any minerals, it just contains H2O molecules. That is what pure water is. So potable water may not be pure, because often potable water contains things that are really good for us, like mineral water. It contains mineral ions, it contains salts, and all sorts of stuff. All right, your tap water, they purposely add fluoride into it because they found that that will help your teeth. All right, so it's not necessarily, potable water isn't necessarily pure. Just be sure that you know that. All right, so a really common question is that they might say, why isn't all potable water pure? Okay. However, you might get asked how you would purify some water. So we're going to come into this in more detail in the second part of the session. But to purify water, one of the ways to make it safe is to make it pure. Right? And the easiest way to do that is through distillation. There are some other methods which we're going to look at, where we're going to sterilize the water to kill anything harmful. But this is the simplest way. So we're just going to distill it. So what you do is you get your water and you put it into your conical flask. The reason why we use a conical flask is because we're going to stick a bung in the top and we're going to put a delivery tube through that bung so that none of the water can escape. We are going to set up the distillation equipment. Again, if you want to write in your method exactly how to set it up, you can, or you can just draw a little sketch. So I've got a conical flask, I've got a delivery tube, right? And then in my delivery tube, that's going into a test tube, which I've got held up with a clamp just to keep it steady. And then that's going into some ice, and the ice obviously is there to cool it down. So what will happen is I'm going to heat it until the water boils, which will be 100 degrees Celsius. That is important and not often talked about enough. Pure water will boil at 100. If you heat your water up above 100, then other things are going to start evaporating too. So obviously what's going to happen here is the water is going to evaporate, it's going to turn to a gas, it's going to travel down the delivery tube, it's going to get cooled down, and it's going to condense, and it's going to turn back into water. And if you did it at exactly 100 degrees, that will be pure water. If you heated it and it was maybe like 104, I'm going to use a different number because that comes up later, 105 degrees, then some other things also might be getting evaporated and also might travel into your water, so it's not going to be pure. Right, so you need to make sure that you are distilling this at 100 degrees Celsius. You collect 1 centimetre cubed of the evaporated water, and then you might get asked just to test it to make sure it is pure. And again, it's the same idea. So if we collect that water, then what we do is we'll boil it with a thermometer in. All right, we might do 3 samples. The boiling point should be exactly 100 degrees Celsius. If it is at a range of boiling points, then you're going to have a problem because you've got something in there that's making it not pure. So if you have managed to do this correctly and this is pure, it will boil at exactly 100 degrees Celsius. Right? If not, impurities will cause a range of boiling points. Again, commonly asked. So, last bit before we take a small break. Some questions. Water that is safe to drink is called potable water. Why is some potable water not pure? All right, and all you need to say is that so safe drinking water may contain, and give an example. So it may contain mineral ions, it may contain salts. Okay, so those things are absolutely safe to drink. All right, it could contain fluoride. Okay, so they wouldn't make it not safe, but it doesn't mean it's pure. So that's the difference. You may be asked how to obtain. Apparently, I can't write. You may be asked how to obtain potable water from unsafe water. So the best way to do that is just talk about how to do it through distillation. So you would say get the seawater, you would place it into a conical flask, you would heat it up to 100 degrees Celsius, you would evaporate it, you would let it go through the distillation tube, you would then cool it back down and condense it, and the condensed water would be pure. You would check that it was pure by boiling it, and if it boiled at exactly 100 degrees Celsius, you know it is pure water. This one's interesting, and they like to link this to the section here about sustainability. One disadvantage of using distillation to obtain potable water, you're going to have to heat it. So heating costs money. So it's worth 2 marks, so you're going to have to explain. So you'd say a disadvantage is that it costs lots of money. The reason why is because in order to distill the water, you have to heat the water to evaporate it. That's why it costs money. Why is that a problem? Well, the issue is that the places where water isn't safe to drink is normally countries that haven't got a lot of money, all right, in order to be spending money on obtaining safe water rather than spending money on food. So that is a problem. So maybe another way is better than distillation. So what else can we do? Well, you can use another method here. So I'm just going to talk about this word desalinization. So seawater, we can make seawater safe to drink. Desalinization, saline means salt. So desalinization just means getting rid of the salts. The way you would do that is you would use something like this. So we have got a partially permeable membrane, hopefully thinking a bit of biology here. We've got high concentration, we've got a low concentration. So we know that during the process of osmosis, water moves from high to low. We are going to use something called reverse osmosis. So we are going to add energy and we are going to move the water from low to high. And all of the water will be able to go through the partially permeable membrane, but the big impurities, which are making it unsafe, or the salts in this case, are going to get trapped. Therefore, we are going to end up with our high concentration of water over here, which is not full of salt. So this is called reverse osmosis. Again, another problem, it requires energy. So I have seen many exam questions where they'll ask you to compare. One of the things in the past that's come up is using solar, so versus reverse osmosis, and this always needs energy. Solar does need energy, but you think about the countries where they might have problems with their drinking water. They're normally hot countries, so actually they can just have a tank in a nice silver tank on top of the roof, which is getting heated by the sun, so it's not costing any energy to them. It's from the sun, and then that will be boiling the water, evaporating the water, and there might be something within that tank which just separates the evaporated water into another area, and therefore you've got some nice pure water that is safe to drink. So you can also do distillation by using the sun, all right, and therefore you cut out the problem of these costs. Okay, last couple of questions. The student's thermometer here in this experiment showed 104 degrees when placed in this fresh water, so when it was in there. Is this water pure? Explain your answer. So 1 mark for saying yes or no, and 2 marks for explaining it. No, it is not pure, and the reason why is because pure water will boil at 100 degrees Celsius. So if this is in the fresh water, and if it was going up to 104 degrees, it can't be pure. There must be impurities within it. How could the student test if the distilled water was pure? Same thing, collect the water and they would boil it. If the boiling point is exactly 100 degrees each time they do it, then they know that it's pure. If the boiling point is a range of temperatures, they know it's impure. And finally, you might get asked to write a method to investigate impurities. Students separated the dissolved solids from a sample of seawater. Describe a method to measure the mass of dissolved solids in a 25 centimetre cubed sample. So, very straightforward. Measure the mass of the evaporating basin on the balance. Pour your 25 centimetres cubed of seawater into your evaporating basin. Heat it so that the water evaporates. Heat it until most of the water is evaporated and you see the dissolved solids appear. leave it to cool, then place it back on your balance with the dissolved solids in. You find the mass of the evaporating basin plus the solids, and you take that away from the mass of the evaporating basin, and that will give you the mass of the solids that were in that sample of water.